Okay, here we are for week 3. This is an intense week. There's a lot of information. There's a lot I'm going to throw at you. A lot of it is built on things you've probably done in high school, or maybe you have a different undergrad, or maybe you're also partnering this with something else. But a lot of these terms should be familiar, and I am going to expand on them and show you how we use them in structural engineering. The kind of premise of what we're talking about today is statics, or the fact that what we're designing, we want to stay still. That's really the point. We don't want our building, when I say stay still, I don't mean move a little bit in the wind. I mean not fly off into space or spin around. So we're going to talk about statics and what it takes to make sure something is static, and then we're going to talk about how we draw those things, and then we're going to do a lot of calculations. The calculations are not embedded. You'll be able to see them in these slideshows, and I'll show you them. But at any point, you can pause this video or leave this video and go watch one of the other ones that have been posted as various example videos, because those I wanted you to be able to look down and see my handwriting as I walked through the lectures. So this video is going to appear to be quite a bit shorter than you might think, but that's because it's expected that you're going and watching those videos as well. So the structural engineer's job, just to remind you, is to make sure that our building is strong enough, stiff enough, and stable. Strong enough. That means it's strong enough in axial loads, so compression or tension, that it's strong enough in shear, that it's strong enough in bending, and that it's strong enough in torsion. Although we're not really going to spend any time talking about that. And that's kind of where we're leading now. The stiffness and the stability, we're going to touch on a little bit. And even today, we're going to touch on the stability, mostly just by reminding ourselves how we draw these things or how we talk about them. So statics. Statics is the branch of mechanics that is concerned with the analysis of loads. So that's our force, that's our moment, and we're going to talk about what those mean on a system. It could be a single beam, it could be the building as a whole, it could be our lateral system that is in static equilibrium. That means it is in a state where the relative position of subsystems do not vary over time, or where the components and structures are at a constant velocity. It stays still. It isn't flying off into space in any of the 3 directions. We tend to talk about our world in a grid system because it makes it a little bit easier to know if we're all talking about things the same way. We can have up and down, left and right, and back and forth. And we often give those things coordinate names like X, Y, and Z. And I'll show you that in a few slides. So if it stays still, every part of it stays still relative to its overall position in space. That doesn't mean a thing that's staying still can't deflect or have movement interior to the system, but that the system as a whole doesn't move around in space. So if we can figure out what it takes for something to stay still, even if we look at little bits of it here and there, it's still, all of those little bits have to stay still. That sounds crazy. I get it. And that's a thing we're going to talk about a lot in the next lecture when we talk about method of sections. But we're going to start to get our head around how we analyze these things in today's lecture. So a lot of the times we're talking about force. Force is something that has magnitude and direction and is represented by a vector. A vector doesn't have to just represent force. It could represent distance, it could represent temperature. There's all kinds of things. It could represent velocity. We can use a vector to represent a variety of things. We are primarily going to talk about vectors in terms of force and moment. Let's start with force because it's really easy to kind of get your head around it. And it's also very linear. You push on something, that's a force. And we're going to start talking about how we think about things. If there's what if we're pushing this way with this force and pushing up with this force? How is that object going to move? Or what do we need to stop that object from moving? So we talked about loads last week, and the unit of force is 1 kilonewton. If you remember, 1 kilonewton is around 225 pounds, roughly. 1 kilonewton is 1,000 newtons. The term newton comes from mass times acceleration. Don't worry about this too much, but 1 kilogram meter per second squared. So we have 1 kilogram of mass times acceleration, which is in meters per second squared, or meters divided by square, or seconds times seconds. And so rather than, that's a kind of a clumsy unit of measurement, kilogram meters per second squared, we've given it a shorthand, and we've given it a name of our wonderful friend who first learned to do these calculations and talked about how we would quantify that value, and we've called it a newton. We often find the values we're talking about have a lot of newtons in it, so it's often easier for us to talk about them by dividing them by 1,000, or moving that decimal place over 3 spots and giving it the prefix kilo, so kilonewtons. Here is an example of a vector. Kind of hard to tell where this is in space. We know it has a value or a magnitude f. F is a valid placeholder to represent a value, but we don't know what direction it is. It's hard to tell because it's really weird looking at it in 3D. So we're going to learn to start to talk about some of that. Now, adding vectors can be done a few different ways. We can use a graphical method that we call tip to tail. So you start drawing your vectors. If you have a series of vectors, you draw your first one. At the tip of the first one, you put the tail of the next one, and so on until you've drawn all of the vectors that you have. And then you say, okay, my resulting vector, or the sum of all of these vectors, starts at the tail of the first vector and ends at the tip of the last vector. And that we could then, if we drew this all to scale, we could have a 2-scale representation of the summation of our vectors. So if we have vector f1, vector f2, and vector f3, and we've drawn them all, we started here, there's the tail of the first one, and then we've drawn f2 from tail to tip, tip, and then our resultant, oh, look, we have one more. Sorry, I can't see my progress slides. If we want to know what the summation of all those is, we start at the tail of this one, all the way up to the tip of this one, and that is the equivalent of adding all of these up. If these were drawn to scale on graph paper, or maybe in AutoCAD or some other means that does really good scale drawings, we could measure this and get the number. We like to do things with math. We like to be able to represent them mathematically, so we're going to need to figure out a way to add these up using math. We can also break vectors down into their components, basically working backwards. We know that it's often kind of nice to work with things in principal axes, like our x and y coordinates. And so kind of breaking these vectors down into their principal axes might be kind of handy for us. So if we had this force here, this vector F, we want to know what its x component is and what its y component is. Now, this, if we're talking about principal axes, that makes this right here a right triangle. If we have a 90-degree point in this, that means we can start to use some of those trig functions that you probably learned in late junior high or early high school, and that we refreshed ourselves with at the beginning of this term, where we have Pythagorean's theorem, and we have our SOHCAHTOA, sine, cosine, tangent of a triangle with a right angle. So if we want to add fx and fy, or these vectors, We want to know what the total force is. It's not a linear addition. We don't just take the value of this and the value of this and add them up. We need to look at different ways to do that. We have a triangle with a right angle, and we know Pythagorean's theorem is the hypotenuse, the square of the hypotenuse, is the equivalent to the sum of the squares of the two other sides, or f squared plus fx squared plus fy squared equals f squared. So if you wanted f, you would then say f equals the square root of fx squared plus fy squared. If we have a right angle and we know one of the other angles, or we need to figure out the angle, we know that the sine of the angle is the equivalent to the opposite side divided by the hypotenuse. We know that the adjacent side is equivalent, the cosine of the angle is equivalent to the adjacent side divided by the hypotenuse. And we know that the tangent of the angle is equivalent to the opposite side divided by the adjacent side. So let's take a look at what this would mean if it was 3D. We often don't work in 3D just because it's a bit of a pain in the butt. But you can see if you draw this in 3D like this, it's hard to tell. Is it in 2D? What position is it in 3D space? So we might need to break it down. But the concept is the same as in 2D. The square of f is equal to the square of fy plus the square of fx plus the square of fz. We're not going to do any work in 3D. I just wanted to show you that the concept remains the same. So what happens if we want to add up non-orthogonal components? That's when it starts to be easiest to break it down into its principal components. So if we want to add f1 and f2, we know we can draw a tip to tail. It starts here and goes up to here. But that doesn't give us a mathematical way to do it. If things are in the same axes, the addition is linear. So if we break f1 into its x and y components, and we break f2 into its x components, we can add up f1x and f2x, and then we can add up f1y and f2y. So you can see here, that's the sum of f1x and f2x, and that's the sum of f1y and f2y, and that is the same as one big triangle to get us our total value for f. So here is that just worked out a little bit. All right, let's take a look at a real example. So this is an example that they've given us where we have three forces, F1, F2, or they've given us three vectors. I shouldn't say force, because look at our units. It's in meters. Doesn't matter that it's called F. Often we use F to represent a force, but whoever's drawn this is a bit of a trickster, and we are talking about something in meters. That is a valid vector way to work it. I have force written there. I'm going to go change this slide. I'm going to update it, change force to vector, just because it muddies the water a little bit. And I don't like that. So I'm going to clean up that slide for you. So we have three forces. I keep doing it. Three vectors. We have F1 equals 10 meters, and they've given us the angle relative to the x-axis here, and they've given us that that angle is 22.5 degrees. They've given us the angle F2. They've given us the vector F2 equals 5 meters, and it is 22.5 degrees from the y-axis. And then over here, pointing in a different direction, we've got F3. And F3 is 7.5 meters, and it is 45 degrees from the x-axis. So let's start looking at this graphically. We can draw it tip to tail. So we've got all three of our forces, and we can draw our resulting force. Look at that. I always get asked, well, how do I know what order to draw these forces in? How do I know? What if you name them Bob, Joe, and Mark? How do I know what order to draw Bob, Joe, and Mark? Doesn't matter. Those are just names. You can draw these three vectors any way you want and still do the tip to tail method. Let's take a look. Let's draw them in a different order. It's the same three vectors, drawn in a different way, same resultant. Let's draw it in another way. Same three vectors, drawn tip to tail, same resultant. So it doesn't matter what order you draw them in. It's not going to make a difference. You're going to get that same value. What's really nice about this is even if you're doing the math version, you can draw yourself a little diagram off to the side. What do I think these values are going to be? It doesn't have to be perfectly to scale, but pretty close to scale, and you'll have an idea of what kind of answer you're going to get. And I always say that everything you need to know about structures you already know. Well, everything you need to know about drawing these diagrams and calculating these things, often inherently, you have a gut feel of what the answer is. So remind yourself of that. Before you do any math, always stop and say, what do I think the answer is going to be? Then go do the math and see if it checks out to what you think it's going to be. So the calculated check, I've gone through and in a video done this check for you. You can pause here, stop here, go listen to that first example, but I go through this exact calculation in detail where you can see me writing out the examples. When you come back, you'll see that these are the answers. So feel free to go check that out. And also the example is worked out here. So you have the actual answer where you don't necessarily have to follow along. You can watch the video, you can look at this, you can try to do it in whatever order you want. Maybe try it out on your own, cross-check with these answers. So equilibrium. Equilibrium, for it not to be moving, if there's forces on it, that means there's something stopping it from moving. And what we want to know is what's stopping it from moving. We want to figure out what those values and what those forces are. Could you do me a huge favor? Yeah. Would you be willing to get me a glass of water? Nice. So everything is subjected to a series of loads. So self-weight, live loads, wind loads, anything. We want the structure not to move or remain in equilibrium. For it to remain in equilibrium, there has to be an equal and opposite force keeping it in place. That would be our reaction. You're awesome, thank you. That's Dave. You're gonna see him in some of the videos. Dave is a brilliant structural engineer. No one ever likes to admit their spouse or partner is smarter than them. Fortunately, it's the burden I have to bear that he's a straight up genius in the same thing I do, but I've learned to live with that. So this equal and opposite force is called the reaction, and that's what's keeping it in place. So if we have something pushing this way and something pushing this way, we probably have something, arrow that way, probably have something acting like this, stopping it. Intuitively, you understand that. I'm going to show you how to mathematically do that. So if this is our force 1, to stop this object from moving, we want the sum of all of the forces to be 0. So we have a force acting on it. We need something that is the opposite to it to not move. Or we want our force plus our reaction to equal 0. Or our force is equal to the negative of our reaction, or our reaction is the negative of our force. We can draw that in there. You can draw it graphically. You can start off that way to get your head around it. I'm going to try to be as consistent as I can, at least in these slides here, where our applied loads are drawn in green and our reactions are drawn in red, just to kind of help us understand what we're talking about. If we have two forces drawn on it, we have F1 and F2, we'd add those up, we'd break it into their X and Y components. Well, they actually already were in X and Y components. We can do the square root of the sum of the squares, find what F1 plus F2 equals. And then we know F1 plus F2 plus the reaction has to equal 0 because we want this thing not to move. We can figure out what reaction we need to stop this thing from moving in space. There you go. Well, what happens if we have ones not along the principal axes and they start to get a little bit more complicated? We've got 3 of them going in this image, all coming into the centroid right here. We can draw tip to tail. We can draw that resultant, and we know we need an equal and opposite reaction to stop this thing from moving. So you could redraw this object like this. We have some unknown reaction that is stopping F1, F2, and F3 from moving this object. We know we could also, if we knew the values of F1, F2, and F3 and what their angles were relative to an axis. I'm a bit lazy. I like to always use the x-axis. It keeps knowing which component is always sine and which component is always cosine pretty easy. You don't have to do it that way, but I will often always do my calculations relative to the x-axis. So let's look at that one that we did earlier, where we had the sum of all of our forces was 14.94 meters, and our angle was 67 degrees relative to the axes. I'm just going to fix that. Bugs me that says sum and not some method of representing angle. We want to know what the reaction is. We know it needs to be an equal and opposite force. So this one was pulling this way. This one has to pull this way. It has to be equal, so 14.94, but in the opposite direction. So let's look at a verbal example. This now, again, is an example that I've worked out in a video. You can pause here. You can go check out that video and take a look at me solving this word-based equation. If you've gone and looked at that, once you come back, you can try working it out on your own. Then you can go look at it, or I have also provided the worked out example here embedded right in the lecture. So you can go about it 3 different ways. You can try it yourself, you can look at it here in the slide, and then you can also go watch the video. So you have 3 ways of kind of tackling this problem. So I want to start talking about another type of vector that we work with, and that is moments. Moments, yes, can also be a vector, and they often will, some of the lingo that we use or the language we use to talk about them are going to help us out a little bit here. You've already heard me talk about centroid a couple times, and that's the center of mass or the center of gravity or the center of inertia of the object. It's the mean position of matter in the body. It's the point about which an object will rotate if it's spinning freely, depending on what thing is loading it. You can have all kinds of neutral axes. The meeting point of all of those neutral axes is your centroid. So if we often use this image to represent a centroid. So if we have this object and we tie the string like that, our neutral axes would be straight through the center of mass. What happens if our centroid is over here, but we hang our object over here? It's going to fall in place until we have a neutral axis passing through our centroid. This thing moves. There's nothing keeping it from moving into that position. When force is applied concentrically to a body, it will move or translate in the direction of the applied force. So if we put a load directly through the centroid, that object will translate, it will slide, it will move. This is assuming there is no reaction holding it in place. So we apply a force, object moves. If we apply a moment about a centroid, it's talking about making the object spin. So we apply a moment and the object spins. If we apply a force, not along the centroid of the object or not along one of the neutral axes, so some distance away from the neutral axes, what do you think? How is this going to move? What do you think is going to happen? Just take a second, think about it. Normally this is where I'd actually ask people to tell me what they think is going to happen. Well, I can tell you it's still got a force pushing it, so it's gonna slide, but it's also going to try to spin at the same time. So we're going to have translation and rotation because we applied our force eccentrically from the centroid. So that seems like there's something interesting happening there. Well, is there anything else that could make the object move the same way? We saw that a force could make it translate and a moment could make it rotate. So a force through the centroid and a moment about the centroid could make it do the same thing. So that means that a force eccentric from the centroid must be equivalent to a force through the centroid and some moment applied around the centroid or about the centroid. So that seems like a handy thing to understand, that we have two ways we can talk about the same movement. A force eccentric from a centroid is the same as the same force through the centroid with some moment causing it to rotate. So let's take a look at that. Moment causes a body to rotate. A force applied eccentrically to a center of a mass causes it to rotate. The farther away the force is from the centroid, the more it wants to rotate. Ignore sliding just for a second. We're going to bring sliding back into it or translation back into it. The further you move that force away, the more the object wants to rotate. And that is dependent on the value E, or what that eccentricity is. So that moment calculation is dependent on the value of the force and the value of the eccentricity. Or we will often say that moment is the product of the force and the eccentricity. Now, here you can see I've included the force through the centroid because we don't want to forget about that. This force is also trying to make the object translate, not just spin. So this moment and a force along the axes is the same as this force some distance from the axes. So let's take a look at some examples. These are just quick ones. We're going to do more complex ones in a few minutes. So this is quick. We're just going to keep this embedded right in the video lecture. So an eccentric force, or P times E, this force eccentric from the centroid, is the exact same thing as this same force through the centroid and the moment about the centroid, where moment is P times E. So these two things are exactly the same. These are equivalent to each other. So if we have this force of 25 kilonewtons, that is 0.5 meters away from the centroid, we know that this would be the equivalent to, if we had the centroid moving this 25 through the centroid, as well as having some moment that causes it to rotate. And we know that that moment or that rotation can have a value of force times eccentricity. Our force is 25, our eccentricity is 0.5, so we would have a force through the centroid of 25 kilonewtons and a moment of 25 times 0.5, or 12.5 kilonewton meters. Remember how newtons had a complex unit system and we gave it its own fun little name? We don't do that with moment. We keep it as kilonewton meters or newton millimeters or kilonewton millimeters. Often we're going to work in two different formats. They can be equal back and forth to each other, but right now we're going to be talking about things in kilonewton meters. And then later in the term, we're going to see that we talk about things in newton millimeters as well sometimes. So our force is going to be 25 still, and our moment is going to be 25 times 0.5 to give us this equivalent system. So these two things are equivalent. This force, 0.5 meters away, is going to try to move this object the same way as this force and this moment. That's kind of handy because making moment connections, or the thing that can resist a moment, remember we need a reaction. So if we have a moment applied to something, we need a moment reaction. Well, moment reactions can sometimes be a pain to detail or create or work with. But pin reactions or force reactions are really easy to work with. You're going to see more about what I mean by that later in the term. So knowing a moment could be equated to a force somehow, could be handy, except that the force wants to also make it move. So how could we talk about a moment using forces that doesn't try to make our object move? A moment all by itself only causes an object to rotate. So how could we talk about that as a force that it only allows the force to make it rotate but not move? And that's where we always give everything fancy names and we talk about the equivalent force couple system. So this moment applied to this object is going to try to make it rotate. This force is going to try to make the object spin in this direction. This force is going to try to make the object spin in this direction, about the central axis here, or about the centroid. So they're both going to cause it to spin in the same direction that this moment did, but look at this. One is going to try to push it this way, and one is going to try to push it this way, and they're going to balance each other out. So this moment only causes rotation, and these two forces only cause rotation. And that's the equivalent force couple system, where these two forces, some distance from the neutral axes, is the same thing as our moment. So both of them are going to try to make this rotate the same amount. So let's look at an example the same way. Again, this is just a quick small example, so I don't have it broken off in a video. If we have force 1 acting downwards at 12.5 kilonewtons, 0.5 meters away, and we have 12.5 kilonewtons acting upwards 0.5 meters away, let's take a look and see how each one causes this to move. This force tries to make the object spin in this direction. This force tries to make the object spin in this direction. Same direction. They both go in the same direction. This force tries to make the object go down, and this force tries to make the object go up. So they're going to balance each other out in translation and only add up to cause the object to spin. So this is the equivalent to one moment on the system. We have 12.5 times 0.5 plus 12.5 times 0.5 equals 12.5. Or these two systems are equivalent. Moment can be talked about as a vector. Now, people always get confused by this, but it's really handy when we need to start keeping track of things being positive and negative. Understanding that moment is a vector can be really handy. Because when we want to talk about moment as a vector, where is it? The moment can be represented as a vector. The magnitude of the vector would be force times eccentricity. The direction of the vector is parallel to the axis of rotation. So this moment is trying to make this object spin about this axis, or trying to spin like this. And we would draw it as an arrow along the axis, and kind of convention when we're talking about moment as a single arrow and not a rotating arrow, we'll put two arrowheads on it. Just so we don't confuse it with force, because it can start to be really easy to kind of confuse those things up. But what's really handy about this is a fun little trick, and I can't see if it's the next slide or not. Well, I should note that moment can be added the same way other vectors are. All the same rules apply. What's really handy about that is something called the right hand rule. If you use your right hand and curling your fingers represents the arrowhead on your moment. So this arrow here, the tips of your fingers represent that arrowhead. The tip of your thumb represents that arrowhead. So if you curve your fingers this way, we would draw that arrowhead for the moment upwards. If our fingers were curving in the other direction, our arrowhead for our moment would be pointing downwards. And that's really handy because when we talk about our coordinate system, we often talk about our principal axes of X, Y, and Z, and we often designate something as the positive direction and something as the negative direction. In our Y coordinate system, which is up and down, up is positive, down is negative. When we're talking about our X coordinate system, the thing to the right is positive and the thing to the left is negative. And for moment, we would apply those same things. If my fingers curl this way around my y-axis, my thumb is pointing upwards, it's a positive moment. If my fingers curl this way around my y-axis, my thumb points downwards and it's a negative moment. And that's going to be really helpful when we start to keep track of things in a little bit. So here you can see just an idea of that. So there are 6 ways a body can move. We can translate up and down, we can translate side to side, and we can translate back and forth. Or Y being our up and down axes, X being our back and forth axes, and Z being back and forth, or left to right, back and forth, or front to back. We can also spin about any of those axes. We can spin about the y-axis, we can spin about the x-axis, and we can spin about the z-axis. So we have translation in x, translation in y, translation in z. We have rotation about x, rotation about y, and rotation about z. Working in a 3-dimensional system can be a bit of a pain, so we'll often try to break it down into a 2-dimensional system, just to make our calculations a little bit easy. We acknowledge that it's an extrapolation or a simplification of the system that is a real 3D problem. Condensed down into a 2D system. If you need to stop and think about it in all 3 planes. But often, the way we're applying our loads, it's simple enough to break it into a principal axis at a time. So when we do that, we'll often say, okay, let's talk about it moving up and down and side to side. We won't worry about in and out of the page. And we won't worry about it spinning about Y, spinning about X. Just worry about it spinning about Z. So we'll restrain translation in Z, we'll restrain rotation about X, and we'll restrain rotation about Y. So what we're left with is, there's another small slide, 38. Should be. So this should be shown as translation in X, or translation in Y, not rotation about Y. So I'll fix that in the slide for you guys. But what we're left with is translation in X, translation in Y, and rotation about Z, or rotation about that axis. And we're going to talk a lot about that. And using your right hand to help represent that is often very handy. Another thing I'll do is I might actually put my finger on the page about the spot I'm talking about and push as if I was the force. And see what direction it makes my page want to spin. And you'll see I do that in one of the mathematical examples. A free body diagram is a simplified drawing of our object or our system that helps us talk about it without getting cluttered down and kind of the busyness of the imagery of it. We just break it down to basically stick figures, sometimes even a dot, and we make sure we look at all the loads that are applied to it, all of the moments that are applied to it, where those occur relative to the system, and then include any reactions that we need to keep it in equilibrium. So we need all the forces, all the moments, all the reactions, and the location of all of those, whether it's in the x coordinate system or the y coordinate system. We need to know where those things take place. So here's an example of a car. Its weight is pushing downwards, and we've got two reactions pushing upwards. We don't know the value of those reactions. We have some intuitive guesses, probably gonna share them equally. This is a really good spot to point out that this is truly a 3D problem, and we've simplified it as a 2D problem. This RF, or front tires, is really two tires. We know that there's a third dimension involved in that. So it would be important to remember that and keep track of that for this system. It can start to get more complex. If this car is parked on the hill and it's in equilibrium, we know that there is some component normal to the tires and some amount that needs to break down the x and y of this force. We need friction to stop this thing from sliding down the hill. So all of these reactions have to exist to stop this weight from making the car move this way or move this way, which really means it would slide down the hill. When we talk about free body diagrams, it helps to know how we draw things. Our coordinate system is x, y, and z. Upwards for y is positive, to the right for x is positive, and out of the page for z is positive. Other people can do other coordinate systems, that's up to you, but in our course and the majority of the world's population use these directions as the positives when we're talking about our coordinate system. A force is often drawn with one arrowhead. Moment or torsion would often be drawn with two arrowheads, or as our circle. Sometimes we'll draw it as the actual circle. Don't worry about this too much, but it is going to come into play, well, even as soon as next week. If we have a series of loads acting on something really tight together, we'll often call it a uniformly distributed load or a stress profile. And that's just saying that we'll often refer to it in kilonewtons per meter, that every meter along the length of this object sees this amount of load. We could rewrite it as one big force, but we'll often spread it out along its length. Free body diagram for the symbols for supports. Our reactions would be arrows. If we have this, which is a pinned support, that's saying it's stopping the thing from moving up and down, and it's stopping it from moving side to side. We'll talk about how we detail these different supports later. I think maybe even in the next slide we touch on it. A roller support only stops movement up and down. It will allow things to roll back and forth. So here's another roller support, but this one's tipped on its side. It stops the object from going this way, but doesn't stop it from rolling up and down. A moment connection is a fixed connection where it stops movement in all 3 degrees of freedom in our 2D system. It stops up and down movement, side to side movement, and that rotation about our Z axes. You see these, for example, at the base of a light post. That would be a moment connection. But they're hard to detail and they're expensive. We don't like doing moment connections if we don't have to. And so often we try to find some other way to deal with this moment. If you guys remember that force couple system, that equivalent force couple system, where instead of a moment, we have forces acting in opposite directions, would be a handy way to then only have forces dealing with reactions, even if we have applied moments. If we're talking about internal systems, we will often draw a pin connection, or where 2 objects come together, where there can be rotation relative to those objects with nothing or with a little dot. If we have something moment connected, which means that it doesn't matter what we do here, those 2 things have to stay at a right angle to each other. Again, moment connections, hard to design. We don't like doing them if we don't have to. We usually represent that with a solid triangle, and that's that's the standard representation of a moment connection. If you look at any drawings that I've posted, if you see that triangle, it means that there is a moment connection happening there. So statically determinate means that we have one restraint for each degree of freedom. We have something restraining our object from going up and down. We have something restraining our object from going side to side, and something to restrain our object from spinning. Remember, that means there's something that's restraining a moment, but a moment doesn't have to be restrained with just a moment. It could be resolved or have a reaction for a force couple instead. So let's look at some free body diagrams. If we had a beam with a uniformly distributed load on a pin roller support, the free body diagram would look like this. We're missing the length here. I think maybe it's fair to add in the length here. Let's add in the length dimension. We would put in a length there, and let's see, do we have all of the means for restraining this? Well, can we stop this from moving in the x direction? Well, at our pin support, it means we do have a restraint in the x direction. The roller doesn't, which kind of seems crazy. Why is one a roller? Why is one not? We'll talk about that going forward. But we do have restraint in the x direction. Do we have something that stops it from going up and down? Well, it looks like we have two things that stop it from going up and down. Both a pin and a roller can provide a support. Now, the last thing is, do we have anything that stops this object from spinning? And intuitively, you might say no. Intuitively, you might say yes. If you were standing up and somebody tried to push you over, you would spread your feet apart. You would open up your feet and put them some distance apart. That's because you intuitively understand force couple systems. And that is exactly what we do here. If there was an applied moment to this system, these two reactions could be used to take that moment out or be the reaction for the moment. We'd have to go through the math. There's work to do with that, but there is something there that could do that job for us. So let's take a look at this pinned roller truss. We know that we can have the reactions that look like that. For a cantilever, this is a fixed condition. So this one we already talked about, that we have all the means to resist it there. Well, we know a cantilever or a moment connection can resolve something in this direction, and rotation. So this one, that one connection can prevent movement for all 3 degrees of freedom in our 2D system. This one starts to look a little bit more kooky. We've got a roller fixed guide. There are engineers that will still say you can't do this. It is hard to detail. We certainly would not want to do this, and I'll show you a funny little quirk with it. So this one, we've got a pin here, so it can't go up and down at this end. There's a roller here, so it can go up and down. We've got a roller in this direction, so this end can go back and forth. But we've got a pin here that stops it from sliding in this direction. But we don't have anything that stops rotation. These two things are along the same plane. We don't really have a couple happening here. But this, if you guys remember, that solid triangle represents a moment connection. So we're saying that even though this can slide up and down, we're going to detail it in a way that it stops it from rotating. This would not be a fun connection. In fact, on the Goldring Center for High Performance Sports, which I shared for the drawings with you guys, we originally had to detail this exact system. And it was, how many days did we spend designing that connection? I think you ended up designing that connection, and it was days for that weird sliding, slotted moment connection.
Oh, yeah.
It was, the owner of one of the most prestigious companies around spent 5 days designing that connection. It wasn't where we wanted to start, but the architect had a very specific set of requirements that we needed to maintain. And this is where understanding communication back and forth between the architect is really important. And they said, no, these are our criteria. We want to maintain these. After we showed them the connection and showed them what it took, they were willing to take away some of those constraints that they had originally put on us. And in the end, it ended up not being this system, but we did start with that system and go through a detail for it. So you can see here, we've got something restraining it here, something restraining it here, and something restraining it from rotating at this end. So how do you detail a roller? What does that roller connection look like? Well, there are two kind of things that can start to happen. First off, what releases moment? How do we not end up with moment either? So moment, we just need to allow some tiny little bit of rotation. Once we have any amount of rotation, that doesn't mean that it has to spin off into space or really kind of rotate a lot. Any amount of rotation means we've released that reaction for moment. The way we naturally detail steel connections looks like this. We have a beam with a little clip angle connected to our column. And as we apply load and this object tries to rotate, or the beam tries to rotate about this point, our angles have a slight amount of prying. They just pull away a little bit from the column. We're talking such a small amount, it would be hard to notice. And this is for your typical normal connections. And once we have that small amount of rotation, we've released the moment. How do we have a roller? Well, for a standard building connection, we will end up having these columns just kick out a tiny little bit. We're talking a fraction of a millimeter of movement often, that will allow us to release that in the X direction, giving us that no restraint in the X direction. This is true for small connections. If we get into a big connection, if this beam came, we're off the page there, if that beam came way down and we had 10 of these bolts to make this work, the idea that that could pry a little bit stops being true. And in that case, if we have a moment connection, we have a moment connection and we have to detail it as a moment connection, or we have to find some other way to detail it to release the moment. The same goes for a roller condition. Now, if any of you have ever driven under an overpass, you often see that the end of the bridge, you can see a break in it relative to its support. In that spot, they actually have Teflon bearing pads that allow the end of that beam or truss or girder to slip just a little bit along that. They'll put guides on it so it can't kind of fly off everywhere. It just allows it to move in the direction we need it to release that condition. Like I said, if you have very special detailing or large things, you might really need to go to the effort to detail that pin or roller condition. If we have a moment connection, it's going to take the moment and we can't have it fail. So we can either detail it as a moment, detail it to release the moment, or we can design it to take the moment. And those are the two options we've got. So equilibrium, we know it's not moving, but we know now it also can't be rotating to be in equilibrium. It can't be going up and down, side to side, or rotating about our Z axes. So a body in equilibrium may not rotate or translate in all the degrees of freedom. That means in our 3D space, all 6 degrees of freedom. To remain in equilibrium, there must be an equal and opposite force or moment to keep it in place. These are the reactions. A really good way to think about it is that the sum of all of the forces or reactions, that shouldn't say rotation, forces, the sum of all of the forces and the reactions must equal 0. So all of the forces trying to push it down and all of the reactions trying to push it up, those added up must equal 0. Everything trying to push it that way and any reaction trying to push it that way, if we sum them all up, has to equal 0. anything that causes it to spin in that direction and anything that causes it to spin in that direction, we have to be able to sum up the rotations and have it equal 0. Remember, moment, spinning it, an eccentric force, spinning it. So we need all of the forces in our y direction to be 0, the sum of all of the forces in our x direction to be 0, and the sum of all of our moments about the z-axis to be 0. So sum of the forces in y, sum of the forces in x, and sum of the moments about z. This is where I move on and do a few examples. I've used a teeter-totter as our base calculation. Most people understand intuitively how a teeter-totter works. If you sit on it by yourself, you're going to drop to the ground. It's going to rotate. That's because the center of our teeter-totter is designed to be a pin. It stops it from going up and down. It stops it from going side to side, but it doesn't stop it from rotating about that point. So an unequal load will cause a moment. Shannon, sitting here all by herself, would have a force and an eccentricity and would cause it to spin. But if the world was blessed with 2 Shannons and the other Shannon sat on the other side of the teeter-totter, the exact same distance away, this Shannon would be pushing down here, trying to spin it that amount. This Shannon would be pushing down here, trying to spin it that amount, and they'd cancel each other out, and the system would be in equilibrium. Or the sum of the moments about the z-axis would be equal to 0. So you'll be able to go look at those slides or look at that video. I think it's video number 3. And you can go and look, or you'll be able to figure it out. It's in there. You'll be able to go through those videos for the example problem sets. And so I'm not going to spend any time on it, but the slides are here too. If you have a hard time seeing it and you just want to hear me talk it through, you've got the slides here. Now, what happens if it's not 2 Shannons, but Dave sitting on the other end of the teeter-totter? Did you know you were in my slides? I apologize. He doesn't normally see these. We've got Shannon sitting on one side and Dave sitting on the other. We all know Dave weighs way more than Shannon, which means he's pushing down with more force. If Shannon and Dave are the same distance apart from the center of the teeter-totter, what do you think is going to happen? Intuitively, no. You put 2 little kids on a teeter-totter, they will figure it out intuitively. You know that Dave, sitting the same distance away from Shannon, is going to try to make the teeter-totter spin so that his bum hits the ground. It's not going to be in equilibrium. So what do you do if you want Shannon and Dave to be in equilibrium on the teeter-totter? You have a few options. Dave could probably move around on the teeter-totter, or Shannon could move around on the teeter-totter. Let's say Shannon is pretty lazy and Shannon just stays in the same spot on the teeter-totter. It would be up to Dave to rearrange his position on that teeter-totter to keep this teeter-totter in equilibrium. So not move side to side, not move up and down, and not spin the teeter-totter about. But we don't know where Dave needs to sit. We can use those equations that says it can't move, that the sum of all of the moments must be 0, to figure out where Dave needs to sit to make this teeter-totter not spin. Again, this is going to be in those example slides. So you can go through and you can see how we work out those calculations. This is where it gets really interesting. If it's not spinning about a point, and it's in equilibrium, that means it's not moving or rotating. It doesn't matter what spot we think about it trying to rotate about. Something that's static is static no matter how you talk about it. It's easy with the teeter-totter to talk about that point where the teeter-totter supports it and sum our moments about that point. But we don't have to use that point. If we want it to be in equilibrium, or we're making it be in equilibrium, we can pick any point we want to talk about. So we can do that same example where instead of spinning it about this point right here, we can imagine we're trying to spin it about Shannon's butt. So instead of trying to spin this teeter-totter about this point, we're going to spin the teeter-totter about that point. Remember, a moment needs a force and an eccentricity to be a moment. If we're spinning this about this point, or imagining we're trying to spin this about this point, the force of Shannon passes through that point. The eccentricity is 0, so Shannon wouldn't cause it to spin. Again, now you can go off and see this calculation in the example set. And now I break off and do a few more examples, essentially talking through the same thing. You can see here we have a beam that has some reactions, and we go through and we solve what it takes for this to be in equilibrium. I always like people to guess where or how much, roughly ballpark, do you think these reactions are going to be? If you look at this beam, where does your gut tell you the reaction will be higher? Do you think it'll be over here at the right end or over here at the left end? And I can imagine, intuitively, you know that if there's way more load over here, this reaction is going to be higher. Sometimes I'll even write myself a little note. I'll write reaction left is going to be less than reaction R, or reaction right. And then I will go through my calculations and see if my answer matches what I intuitively thought. Because if I've made a mistake in my calculations, that little self-check might help me out quite a bit. And then I go through and do 2 more calculations using beams, just fun beams as an example. So it was a lot of information. You have all of those example slides to go through. Take your time, think about your calculations. You're gonna do calculations in your assignment. You have a week to do those calculations. Stop, talk about it with your friends. That's what it's for. We're gonna be monitoring that discussion board, but feel free to talk about how you solve solutions conceptually. Maybe don't write the answers out for someone, but you can talk these things through with each other. So remember, everything needs to be strong enough, stiff enough, and stable. Statics, everything stays still, even though we know that there's internally some movements, like how do you explain deflection, for example. But we're not talking about the internal movement, we're talking about the object as a whole, flying off in space or rotating. If it's staying still, it means it's in equilibrium. If it's staying still in equilibrium, there must be reactions. And we have those reactions for force and moment, and we can use an equivalent force couple system to resolve moments using only forces. And we know that we can use a free body diagram to help us draw that, to help us start doing our calculations. And we know that if an object is static, that we mean it's in equilibrium, that we can use any part, we can look at any part of it being static. So we can sum those moments about any part as long as we know that that thing is going to be static, or to figure out what it takes for that to be static. So I know it's weird having this lecture broken up into separate kind of little modules, but there's something kind of clean about it that I think you can stop and take a break and look at your calculations. You can listen to kind of the theory about it and then go off and do the calculations or try them yourself. So that's the end for lecture 2. It was a lot of information. Feel free to Google more kind of examples on the internet. Remember, if you're looking at forces and things like that, codes might be different. The statics, or the kind of the science and the mathematics behind this, doesn't have any dependence on codes. But if something starts to refer to what the value for particular loads are, for example, that might be code dependent. But the method and the math for this is totally fine to use kind of anything, anywhere. In fact, the way I always did this when I went through school, the book we used was that statics book that I said was very expensive and I'm not going to make you guys buy. And it's, 300 pages of problem solutions, problems and some solutions. But sometimes they use buildings and elements within it as an example, and anything that was code related ended up getting a little weird because it wasn't our code. So we had to learn the kind of method to do it, but make sure we understood that it wasn't our code. So feel free, go look up more examples, knock yourself out, and I've given you kind of 6 worked out problems, the 3 different teeter-totter versions, and the 3 beams that you can look at. Make up your own beam. Try to solve your own if you'd like. That's totally good too. So have a good day, and I'll see you guys next week.